Today we want to talk about the basics of some of the most important electronic circuits. Without them, there would be no TV, no radio, and data transmission would be a very difficult task to achieve. I'm talking, of course, about electronic filters. Electronic filters come in a variety of different forms. They can be active, passive, analog, digital, linear, non-linear, high pass, low pass, band pass, band stop, all pass. To get the hang of it all, we want to start with one of the simplest and maybe most important circuits, the passive analog filter. First of all, what is an electronic filter? An electronic filter is used to remove unwanted frequency components from a signal. We can differentiate between two main types of filters, the low-pass filter and the high-pass filter. As the name suggests, the low-pass filter lets low-frequency signals pass through and blocks only signals with high frequencies. In contrast to the low-pass filter, the high-pass filter will let high-frequency AC signals unaffected, hence high-pass, while it will filter out low-frequency signals. Electrical engineers will often look at this behavior from another perspective, or, mathematically speaking, from another domain, the frequency domain. We can plot the amplitude of an AC signal over its frequency. The amplitude is depicted on the vertical axis and the frequency on the horizontal axis. Typical double logarithmic scaling is used for this kind of plots. A perfect low-pass filter signal would look like this. For low frequencies, the signal passes through unaffected until the so-called corner frequency Fc is reached. Everything above this corner frequency is being blocked by the low-pass filter, so the amplitude becomes zero. The high-pass filter will do just the opposite. It will remove all low-frequency AC signals until the corner frequency Fc is reached, while all signals with frequencies higher than Fc will pass through unaffected. We call those areas where AC signals can pass through the pass band, and those where AC signals are stopped, the stop band. We can also build combinations of low pass and high pass to get two more types of filters, the band pass and the band stop filter. These types simply have two corner frequencies, between which lies the pass band or the stop band respectively. Notice that until now all AC signals can either pass through our filter or are simply stopped by it. There are filters though which can actively amplify an AC signal. We will talk about those so-called active filters in one of our next video. But today we only want to focus on how to build passive filters. We have already seen how ideal passive filters should behave, but like always, the real world is a little more challenging. To start out easy, we will need only two elements for our passive filter circuit, which is a resistor and a capacitor. With only these two parts, we can build a so-called RC filter. To grasp the basics of an RC filter, just think of a simple voltage divider, where the output voltage is always a fraction of the input voltage, depending on the impedance of the two resistors. Mathematically speaking, we could say that the output and input voltage behave like their respective impedances. If we take two ideal resistors, the circuit is not frequency dependent. It will do the trick for either DC signals or AC signals regardless of their frequency. In the next step, we can make this circuit frequency dependent by simply exchanging one of the resistors with a capacitor. That's because the capacitor has a very interesting characteristic. Its impedance will change with frequency. This correlation can be expressed mathematically by the following formula. Zc is minus J divided by omega times C, where J stands for the square root of -1. Mathematicians call this number the imaginary number I, but in electronics the lowercase I is reserved for an AC current. Therefore, we call it J. Omega is the angular frequency and equals 2 pi times the signal frequency f. And finally, C is the value of the capacitance of our capacitor. Let us forget about this strange constant J for the moment and let's focus on what the equation tries to tell us, namely that the impedance gets smaller with higher capacitance and, more importantly, it gets smaller with higher frequencies, and that's exactly the attribute we'll be using to build our filter. Let's take a look at what our RC filter does at the two frequency extremes. If the signal frequency is 0, or in other words, if the input voltage is a DC voltage, the impedance of the capacitor will theoretically approach infinity. We can therefore exchange the capacitor with an open loop. Since no current can flow to ground, the output voltage will be the input voltage. For the other extreme, if the signal frequency is close to infinity, the impedance of the capacitor will drop to 0. We can therefore think of the capacitor as a short circuit. The output voltage is pulled to ground and will therefore be 0. At this point, you might want to take a little time to ponder over this other circuit. Do the same thing as we did before and think about what the output voltage will do at the two frequency extremes. For now, I'd like to focus on our first RC filter. In summary, we can say that on the one hand, a high frequency input voltage will cause the output voltage to drop to 0, while on the other hand, any low frequency input voltage will be passed to the output. A low-pass filter is born. We now know that at the frequency extremes, our filter will behave just the way we want it to. But what happens in between those extremes, and where is our corner frequency Fc? To get to the bottom of this, we again need to think of our filter as a frequency-dependent voltage divider. If we want to know the frequency behavior of a filter, we actually want to know the answer to the following question. What does the output do in dependency of the input? In other words, we want to know what is the output voltage Vout divided by the input voltage Vin. As we already know from the voltage divider, this relation can be explained in terms of the respective impedances. In order to solve this equation, it is finally time to deal with those J's. For this, we need a little more knowledge about our capacitor and a neat mathematical trick. We first have to know that for every sinusoidal signal, the voltage across an ideal capacitor and its current are always minus 90 degrees out of phase. But why is that? A static description of the behavior of a capacitor would say Q is C times V, where Q is the electric charge inside the capacitor, C is a measure of how big the capacitor is, and V is the voltage across it. If we want to have a relation between current and voltage, we need to differentiate the charge with respect to time. We assume the capacitance C to be constant. On the left side of the equation, we get electrical charge per time, which is equal to current. On the right side, we get C times dV over dt. This resembles the dynamic behavior of a capacitor. One way to think of this equation is to imagine the capacitor as a water tank with area C and height V. The volume Q of the water is simply C times V. If you fill the tank with a big hose, or in other words, a big current I, the water level V will rise quickly. If you fill it with a little straw or a small I, the water level will rise slowly. A big tank with large area C will take, of course, longer to fill than a small tank. A good mathematician will immediately see that the phase shift between voltage and current comes from the derivative. If we plug in a sine-shaped voltage V into this equation, the current will always be cosine, hence minus 90 degree phase shifted. With our new knowledge about the capacitor, we can revisit the RC filter. The fact that current and voltage at the resistor are always in phase, while current and voltage at the capacitor must be 90 degrees out of phase, leads to another interesting circumstance. Since the same current I is flowing through our resistor and our capacitor, this must mean that the voltage across R and C are also minus 90 degrees out of phase. Or, in other words, we can say that their impedances are minus 90 degrees out of phase. Now this is probably the moment where you might ask, what does all that have to do with our filter? Well, it's time to bring all of it together by introducing the phasor diagram. The phasor diagram lets you compare amplitude and phase of the input and output of a circuit. The diagram uses horizontal axis called the real axis, which represents the impedance of a resistor with no phase shift. The vertical axis is called the imaginary axis and represents impedances with a 90-degree phase shift, like our capacitor. If we remember our formula for the impedance of the capacitor from before, suddenly all should make sense. The mysterious imaginary number J in front of the equation shows us that the impedance must be denoted on the vertical axis with a length of 1 over omega c. We also notice the minus sign in front of the imaginary number J, which shows us that the impedance of a capacitor is negative. Watch how the length of Zc increases with low frequencies, while it decreases for high frequencies. It's just a graphical representation of what the capacitor does. Its impedance is minus 90 degrees phase shifted and increases at low frequencies, while it decreases at high frequencies. Remember that the impedance of the capacitor determines the voltage at the output of our filter. With the phasor diagram, we can also calculate the sum of the real impedance of the resistor R and the imaginary impedance of the capacitor Zc. We simply have to add both vectors graphically. The result is the vector Zin, which has a length as well as an angle. This impedance Zin is of course proportional to the input voltage. Now we finally have all the things we need to describe the behavior of our filter at any frequency of our input signal. We can assume an arbitrary value for R and C and simply measure the length of the vector Zc and Zin. The angle of Zc will of course always be minus 90 degrees, but the angle of Zin will get smaller and smaller for higher frequencies. We can calculate V out over V in by simply dividing the length of the vector Zc by the length of Zin. This will give us the so-called attenuation of the filter. As you can see, it is the same representation as the ideal filter behavior we have seen at the beginning of the video, but shows us the ugly truth. In the real world, the slope at the corner frequency of our filter is far from infinite. Instead, the attenuation of our real-world low pass decreases painfully slow. For a steeper slope in attenuation, we need higher order filters, which we will discuss in our next video. Today, we will limit ourselves to first-order filters. Additionally, our filter not only attenuates the amplitude of the input signal slower than expected, but does also apply a phase shift to it. If we divide a phasor Zc by Zin, we can also obtain this second plot. Mathematically speaking, a division of two phasors yields a division of their lengths and a subtraction of their angles. This might seem a little weird, so we calculate one particularly interesting point together. Let's assume a signal frequency where the impedance of our resistor and our capacitor are exactly the same. This will lead to an angle of minus 45 degrees for Zin. If we want to calculate the angle of V out over V in, we have to do the following subtraction. The angle of Zc minus the angle of Zin is minus 90 degrees minus minus 45 degrees, which is equal to minus 45 degrees. This point of the plot is very special because it is exactly where our corner frequency Fc is defined. If we want to calculate the attenuation at this point for an arbitrary length a, we can apply the law of Pythagoras. As a result, we now know that at the corner frequency Fc, the output voltage of a real filter is always 1 over the square root of 2 times the input voltage. This whole representation of attenuation and phase shift is called the Bode plot and is most commonly used to describe the behavior of a filter circuit. You will often see that the horizontal axis of the Bode plot is logarithmically spaced in order to depict a large bandwidth. Additionally, the vertical axis is usually labeled in decibels, which is why the corner frequency is often called a 3 dB point for first-order filters, since 1 over the square root of 2 is minus 3 dB. The minus is often dropped in technical slang, since we don't want to be too squeamish. In this first video about analog filters, we have discussed the basic concept of an RC low-pass filter. But, as you might guess, there's a lot more to know about these handy little circuits, which we will discuss in our next video. I'm Michael with the Institute of Electronics. I hope you've learned something today, but anyway, thanks for watching. If you want to learn more about analog filter circuits, we highly recommend The Art of Electronics by Horowitz and Hill, as well as Elektronische Schaltungstechnik by members of our institute.